Hello students, we begin with another part of our first unit, that is countability and uncountability of sets. So we will deal with counting the number of elements in a set and defining what is a finite set, what is an infinite set, what are countable sets, uncountable sets. So before going into the mathematical details, just let us try to visualize how we count objects. So let us see this small animation here. Say we want to count some objects which are contained in that box. In order to count, we use numbers or natural numbers 1, 2, 3, 4, 5, 6. These are called the counting numbers, right? So suppose we have some elements here, say an apple and a book in the box. So there are two objects here. So how do we count? We designate this apple by 1 and the book by 2, right? So there are two objects, right? Suppose I include another third object here. Suppose a car comes out from that box. So in order to count the number of objects, now we need another number. So we go on with the next number, that is 3. That is the next number. So we have in the first line we have a set of objects, and in the second line we have the set 1, 2, 3. Okay, so if there are 3 objects, we count them using the numbers 1, 2 and 3. So mathematically speaking, we are constructing a bijective mapping, that is 1-1-1-2 mapping between the objects and the numbers 1, 2 and 3. Okay, so this way, say if we have another object, we use the next number, that is 4. So there are 4 objects, right? Suppose we have another object now, so we will use another number, that is 5. Okay, so that way the counting process goes on. So mathematically you can see what we are doing is we are just constructing a bijective mapping between the set of objects and the set of numbers 1, 2, 3 up to n. If there are n objects, we are creating a bijection between the set of objects and the set of natural numbers, the set of first n natural numbers 1, 2, 3 up to n. Okay, so this was an illustration. Now let us go into the mathematical details. So countability and uncountability of sets. So we consider the set ABC, just the example that I had given with apple, book and car. So how do we count the elements of this set? We start the usual way with 1 and keep on counting serially up to 3. So we stop after 3 as we have exhausted the set. Okay, so mathematically we have just created the following bijection. So from the set 1 ABC, we create a bijection to the set 1, 2 and 1, 2, 3. So the element A goes to 1, that is f of A equal to 1. Element B goes to 2 and element C goes to 3. Okay, we could have done it other way also. A goes to 3, B goes to say 2, C goes to 1. That is also a bijection, no problem. So there are several ways of counting. So ultimately, to count the number of elements in a set, we create a bijection from that set to the set of first n natural numbers. Okay. So this motivates the following definition. A set S is said to be finite if it is either empty or there exists a bijection from n suffix n, that is the set of 1, 2 up to n, the first n natural numbers, to S for some n belongs to natural numbers. Okay, so a set is said to be finite if it is either empty or we can construct a bijection from 1, 2 up to n to the set S for some natural number. So in this case, when there exists a bijection from 1, 2 up to n to S, we say that the set S has n elements. Okay, so since inverse of a bijection is also a bijection, so the existence of bijection from 1, 2 up to n to S is equivalent to existence of bijection from S to 1 to up to n. So both are equivalent. Okay, so the set will be said to be finite if it is either empty or there exists a bijection from S to 1 to up to n, which is equivalent to getting a bijection from 1 to up to n to S, the other way around. Okay, because in your first semester itself we have done that the inverse of a bijective mapping is also bijective. So note that a set is said to be infinite if it is not finite. That means if it is not possible to construct any bijection from 1 to up to n to the set of natural the set in question for any natural number n. Okay, so there is no natural number n for which there is a bijection from 1 to up to n to S. In that case, the set is said to be infinite set. So the above definition of finite sets gives the following two results, which are quite obvious, but since we have defined the sets formally, finite set formally, we need to derive this result from our definition. So if S is a finite set, then the number of elements in S is a unique number. That means when S is a finite set, so the number of elements in S is that value of n for which there is a bijection from 1 to up to n to S. So we need to show that there cannot exist two different values of those n. Okay, so we observed that if n is greater than m, then there cannot exist any bijection or there cannot exist any 1-1 map from nn to nm. Okay, so if there are more elements 1 to up to n, so say you cannot construct any bijection from the set 1 to up to 10 to the set 1 to up to 5. Okay, this cannot be done. Why? So the explanation is basically quite simple, and it can be explained with the help of Pigeonhole Principle, which states that if there are k plus 1 objects which are to be placed in k boxes, then one of the boxes will have more than one object. Okay, it's you try to understand this line. If k plus 1 objects are to be placed in k boxes, then one of the boxes will have more than one object. Okay, why is this so? This is because if all boxes have at most one object, then the total number of objects is at most k, but it is given that there are k plus 1 objects, so it cannot happen that every box is having at most one object. At least one of the box should have more than one object. Okay, so in general, if n objects are to be placed in k boxes where n is strictly greater than k, then one of the boxes must have more than one object. Okay. So it's a very important principle in combinatorics. So constructing a function from 1 to up to n to 1 to up to n is like placing n objects 1 to up to n in m boxes. So this 1 to up to small m, this can be regarded as boxes. So placing the image of A, finding the image of A is like placing this 1 in this box. Finding the image of 2 is like placing 2 in this box. Okay, so in this box or any other box, right? So we can apply Pigeonhole Principle here. So if n greater than m, so two elements say I and j of n will be placed in the same box. That is, they will have the same image, right? If n is greater than m, so at least one of these boxes will have more than one object. That means what? Two elements from the first set have been placed in the same box. Hence, that means two different elements will have the same image. So the function cannot be 1, 1. Right. So now suppose, so we have shown that if n is greater than m, there cannot exist any 1, 1 mapping from nn to nm. Okay. So now let us show that if S is finite, then S has unique number of elements. Okay. So now suppose that S has n elements, so there exists a bijection. So this is our definition. There exists a bijection from nn to S. Also suppose that m has m elements. Okay, somebody else gets S having m elements, somebody else gets another bijection. Okay, so we need to show that no matter which bijection you take, every time this n and m will be equal. Okay, so we have to prove that m is equal to n. So by law of trichotomy, which we had discussed, given any two real numbers, only exactly one of the following is true: m is less than n, m is equal to n, or m is greater than n. So if let m is less than n, then since G from Nm to S is a bijection, okay, because we had supposed that S has M elements also, so G inverse is also a bijection. So you consider the composite map G inverse OF, which is a map from Nn to Nm, then this is also a bijection by properties of bijective mapping. So it is a 1-1 map. That means I have gotten 1-1 map from Nn to Nm even when N is greater than M. Okay, but that cannot happen because N is greater than M. So there cannot exist any bijection. So in particular, there cannot exist any 1-1 map. So M less than N is not possible. Let M is greater than N. Then since F from Nn to S is a bijection, so F inverse from S to Nn is also a bijection. So F inverse OG, that is the composite of F inverse with G, it is a map, bijective map from Nm to Nn. Okay, so it's a bijection, and so it's 1-1. But M is greater than N, and we know there cannot exist any 1-1 map from Nm to Nm. Nm to Nn. So M is greater than N is not possible. So the only possibility is that M equal to N. So that is S has unique number of elements. Okay, so that is why we can define the number of elements. And say N is a finite, N is an infinite set. Okay, so let us prove this also from definition. The very basic infinite set that we have. So it is enough to show that for each N belongs to natural number, there cannot exist any bijection from N to Nn. Whatever N we take, small n we take, we can never find any bijection from the set of natural numbers to the set of first n natural numbers. Okay. So suppose that there exists a bijection from N to Nn, then F is a 1-1 map. Okay. So and let you take small m equal to n plus 1, then the restriction of F to the set of first m natural numbers is also 1-1. Okay. If F from A to B is 1-1 and C is a subset of A, then F from C to B is also 1-1. Okay. That follows from the definition of subset itself, because for you take any two elements X and Y in C, right, which are unequal, then X and Y are also elements in A, so and they are unequal, and since F is 1-1 from A to B, so Fx is not equal to Fy, right. So if F from A to B is 1-1 map and C is any subset of A, then F from C to B, that is also a 1-1 map. Okay, so this concept we have used. Restriction of F to Nm is also 1-1. So that is, we get a 1-1 map from Nm to Nn, but by pigeonhole principle already we have shown that there cannot exist any bijection from Nm to Nn. So in particular, there cannot exist any 1-1 map from Nm to Nm. Okay, so we have got a but this is not possible. Okay, so hence there cannot exist any bijection from N to Nn, right. Since there cannot exist any 1-1 map, so there cannot exist any bijection. Okay, because bijection is 1-1 and onto, so N is infinite. Now let us see another theorem which may not be that important from the exam point of view, but it's very important to understand this concept in order to deal with these bijective mappings for countability and uncountability. Okay, so let us try to understand this. If A is a set with m elements and B is a set with n elements, and A intersection B is empty, that is A and B are disjoint, then A union B has exactly m plus n elements. Okay, so this is also called the addition rule of counting. This theorem, this first part, this is also called the addition rule of counting. And if A is a set with n elements and C is a subset of A that has and C subset of A has one element only, then A difference C has n minus 1 elements. Okay, so that is a variation of or a type of subtraction rule. Okay, subtraction rule for counting. Okay, and then if C is a infinite set and B is a finite set, then C difference B is always infinite. Okay, So if we take the difference of infinite set and a finite set, then we get a infinite set only. So let us try to prove it one by one. So since A has m elements, so there exists a bijection from nm to A, right? And since B has n elements, so there also exists a bijection G from nn to B. Okay, so we define a new function which is from m plus n to A union B as h of I equal to f of I if I lies between 1 and m, and if I is lying between m plus 1 and m plus n, we define it to be g of I minus m. Okay, so we show that h is nothing but 1 1 and 1 2, so it's a bijection. Okay, so we start with I and j inside n m plus n such that I and j are unequal. So in order to prove that a map is a bijection, we need to start with any two arbitrary elements x and y of the domain which are unequal, and then we have to show that the images are also unequal. That is, distinct images, distinct elements have distinct images. Okay, that is the definition of bijective 1 1 map. Okay, distinct elements have distinct images. So that is why we start with I and j inside n m plus n such that I and j are unequal. Okay, so there are several cases. It may happen that both I and j are lying between 1 and m. Okay, so why we are considering these cases? Because the function has two different definition. One part is for I lying between 1 and m, another part is for I lying between m plus 1 and m plus n. Okay, so if I and j both lie between 1 and m, then h of I is f of I, h of j is f of j. But since f is 1 1, so I not equal to j will imply fi is not equal to fj. Okay, so this will imply that hi is not equal to hj. Okay, then another case, it may happen that I and j both lie between m plus 1 and m plus n. In that case, h of I will be g of I minus m, h of j will be g of j minus m. So since I is not equal to j, so I minus m is also not equal to j minus m, and since g is 1 1, so g of I minus m is not equal to g of j minus m. Okay, so thus h of I is not equal to h of j. Another case that is left is I lies between 1 and m, and j lies between m plus 1 and m plus n. Okay, in that case, h of I is f of I, h of j is g of j minus m. So since h of I, we see that h of I belongs to A, right? Because f is a function from nm to A, and h of j belongs to B because g is a function from n to B. Okay, so but A intersection B is an empty set. That is, A intersection, there cannot be any common element between A and B. That means what? Hi and hj cannot be equal, right? Since there is nothing common, hi is an element of A, hj is an element of B. If they are equal, then A intersection B becomes non-empty. But it is given that A intersection B is empty, so hi and hj cannot be equal. Okay. So similarly, if j lies between 1 and m, and I lies between m plus 1 and m plus n, then hi is not equal to hj. So in all cases, I not equal to j will always imply hi is not equal to hj. So h is a 1 1 map. Okay. Next I have to show that h is onto. So we start with an arbitrary element in the codomain. So let y belongs to A union B be any element. Since A intersection B is phi, so either we have y belongs to A or we have y belongs to B. So there are two cases. So if y belongs to A, then what happens? Since f from nm to A is a map, or is a 1 onto map, so there exists an I inside nm such that f of I is equal to y. Okay, but since I belongs to nm, so that means I lies between 1 and m. So in that case, f of I can also be written as h of I, right? So we have got an element I inside. So let me just mention it here. We have got an element where I is in the set n m plus n. Okay, n of m plus n. Right. So where I is in the set nm plus n. Right, so we have got an element which of the set n m plus n. Since I is lying between 1 and m, it also belongs to this set. So h of I equal to y. So we have got an element in n m plus n whose image is y. The second case, if y is in B, then g since g from nn to B is onto, so there exists an I inside nn such that g of I is y. Okay, but I lies between 1 and n. That means m plus 1 will I plus m will lie between m plus 1 and m plus n. So h of g of I can be written as h of I plus m. Okay, and so h of I plus m is equal to y. Thus in both cases y has a pre-image. So we have got pre-image in both the cases in n m plus n. Hence h is onto. And thus h is a bijection, and so A union B has m plus n elements. Okay, so this is the proof. Now the next one, since A has n elements, so there exists a bijection f from nn to A. Let C equal to singleton x. So it's a set having one element, so we take C as singleton x, which is a subset of A. So there exists some j in nn such that f of j equal to x. Okay, so we construct a function g from n minus 1 to a minus c as this. G of I will be equal to f of I if I is less than j, and equal to f of I plus 1 if I greater than or equal to j. Okay, so in diagram you can see what we are doing is we are taking all elements which are less than I to their original images, and since I is skipped, so we are taking the image of I to f of I plus 1. Okay, because f of I is not there in the new set, right? So that way we construct the element. So g of I will be equal to f of I plus 1 if I greater than or equal to j. Okay, so since since g is 1 1, I have to prove that g is 1 1. So let p and q belongs to nn minus 1. So this is the new domain we have, new domain of the new function, and p not equal to q. Okay, so we start with p not equal to q. So there are several cases. It may happen that both p and q are less than j. So in that case, gp is same as fp and gq is same as fq. And since f is 1 1, so p not equal to q will imply that fp not equal to fq. But fp is same as gp and fq is same as gq. So gp is not equal to gq. Then it may happen that p is less than j and q is greater than or equal to j. So in that case, what will happen? G of p will be f of p, but g of q will be q plus 1. Now p is less than j and q is greater than or equal to j. So q plus 1 is strictly greater than j, right? So p is a number which is strictly less than j and q plus 1 is a number which is strictly greater than j. So obviously p and q plus 1 cannot be equal. Okay. So and since f is 1 1, so f of p is not equal to f of q plus 1. So g of p is not equal to g of q. Okay, again another case, if both p and q are greater than or equal to j, then we have g of p is f of p plus 1, g of q is f of q plus 1. But p not equal to q, this will imply that p plus 1 is not equal to q plus 1, and since f is 1 1, so f of p plus 1 is not equal to f of q plus 1. That means gp is not equal to gq. So in all cases we get p not equal to q implies gp not equal to gq. So g is a 1 1 map. Okay. Next is g is onto. How to show that g is onto? Let y belongs to a minus c be any element, then y is not equal to x, right? So since f from nn to a is onto, so for this y there will exist an I inside nn such that f of I is y. Okay, now what I have to show? I have to show that this or I have to find some I or say some p inside n minus 1. Okay, because our domain is n minus 1. So since y is not equal to x, one thing is sure, that I is not equal to j. Okay, So because if I equal to j, then fi will be fj, so that is fi will be equal to x, so that is not possible. Okay, because y is not equal to x, we had already taken, right? So what was j? J was the element for which fj is equal to x. Okay, so either I is less than j or I is greater than j. If I is less than j, then what will happen? I belongs to this set, obviously. Okay, because yeah, I is strictly less than j, so the maximum value of j here is n, and so I cannot be equal to n because I is strictly less than j, so I belongs to this set 1 to up to n minus 1. So this is the set n minus 1, and since and so f of I is same as g of I by definition, right? If I is less than j, then fi is same as g of I is same as f of I. So ultimately we have got g of I is equal to y. If I is greater than j, then as I less than or equal to n, so I minus 1 will be less than or equal to n minus 1, right? So I minus 1 is an element inside 1 to up to n minus 1, which is n minus 1, and also I greater than j will imply I minus 1 is greater than or equal to j. Okay, so g of I minus 1 will be same as f of I minus 1 plus 1. Okay, because if I is greater than or equal to j, the definition was g of I equal to f of I plus 1. So g of I minus 1 will be equal to I minus 1 plus 1. Okay, so it is f of I, which is y. So thus in all cases, for each y belongs to a minus c, there always exists some p. So in the first case p was I itself, in the second case p was I minus 1. Okay, such that g of p is same as y. Okay, hence g is onto, so thus g is a bijection and a minus c has n minus 1 elements. Okay, the last one, given c is an infinite set, so there cannot exist any bijection from n to c for any n. So given b, also it is given that b is a finite set, so let b has n elements. Now suppose that c minus b is finite and has m elements, then we know that the intersection of b and c minus b is phi. So by the first result, b union c minus b will be a finite set which will have n plus m elements. That is, but b union c minus b is what? It is the set b union c difference b. It is just the set C. Okay. Sorry, I have written something wrong here. Intersection of B with C minus B, yeah, it's empty, and then B union C minus B is a finite set which is having n plus m elements. Okay, so that is so this means that B union C intersection B complement. So B union C, so that is B union C is a finite set. Okay, yeah. So that is here it will be B union C. B union C. That is please correct it. B union C will be a finite set. That is B union C is a finite set having n plus m elements. But this contradicts the fact that C is infinite. C is an infinite set, so C union B cannot be a finite set. Okay, hence C minus B has to be infinite. Okay, so this was the proof. So it was given that C is infinite set, and we had supposed that C minus B is finite. Then by the first result, B union C minus B is also finite. So B union C minus B is B union C. So it is given that B union C is a finite set. So but this contradicts the fact that C is finite. Okay, so why does it contradict? If B union C is finite, that means there exists a bijection from B union C to n m plus m for some n plus m, right? And the restriction of F on C will also be a 1-1 map. So there exists a 1-1 map from C to n plus m. Okay, that is why, but that is not correct because C is infinite. Okay, so that is the reasoning. Maybe I missed this line here. I should have written it. Okay, still you try to write it yourself. That B union C is finite. That means what? There exists a union C is finite means there exists a bijection from B union C C to n plus m. There exists a bijection from B union C to n m plus m, but in that case, so the restriction of F on C, which is a subset of B union C, is also 1-1. Okay, 1-1. And so it's not possible, and it is not possible. It's not possible as C is infinite. C is infinite. Okay. So that will justify our reasoning. Okay. Right. So in the next lecture we will be studying countable, uncountable sets and some properties of these finite sets. Okay. Thank you.